Hi, this is part 3 of the term 3 review. We've got a graph of velocity now, and we're told that these are the values there, and we're also told that the area of these from 0 to 3, that area is 8, this area is 3, and this area right here is 2. Okay, so we'll use those as we go. A says, when does the particle change direction? So in order to know if we change direction, what we're curious about is, do we have a place where the velocity switches from negative to positive? So for example, start off, we have a negative velocity from 0 to 3. That means we were traveling to the left during that time. At the time 3 seconds, we switch, and now we have a positive velocity and we're moving to the right. So at t equal 3, we change direction, and then again at t equal 5. And that's where v of t switches sign. B, on the interval 2 to 3, is the speed increasing or decreasing? So from 2 to 3, notice how our velocity is getting closer and closer to 0. And because the velocity is getting closer to 0, we would see, like if we had a measuring device, we'd see it getting closer and closer to 0. So we'd be slowing down. Right? Our speed would be decreasing. But maybe another way of explaining this is the velocity during that time is negative because we're below the x-axis. So velocity is negative. But the acceleration is positive, and I know that because the velocity is increasing. So it's a situation where the velocity in that time is increasing, but the speed itself is decreasing. We're in a negative velocity, heading towards 0, which means the speed goes down, and then heading towards a positive value, which means the speed's going up. So two different ideas. Velocity the entire time is increasing, but speed goes from decreasing to increasing. During what time, if any, is the acceleration of the particle negative? So we'd have a negative acceleration when velocity is decreasing. This is the velocity, and this was decreasing from 0 to 1 and from 4 to 6. So from 0 to 1 and from 4 to 6. And again, that's just velocity is decreasing. Find the average rate of change of the velocity from 0 to 6. So from 0 to 6, we went from a velocity of 0 to a velocity of -2. So the average rate of change is just simply the slope of that line. The velocity went down 2, and it took 6 seconds to do that. So the average rate of change of the velocity is -2 over 6. Now, another way of thinking about that is, what was the change in velocity? V of 6 minus V of 0 over the change in time. Okay? That's another way to kind of think about that. And since it's the rate of change of velocity, this would be in units of acceleration. So if they gave us some units here, if it would say feet per second, then this would be feet per second squared. Right? It'd be an acceleration unit. Whereas E is find the average velocity from 0 to 6. Now we're going 1/6 times the integral of the velocity, which is going to be 1/6 times the sum of the areas. Now, because it's just velocity, we have to treat these as negative areas. So it'll be -8 plus 3 minus 2. And this is going to give us a -7/6. And again, this would be in terms of feet per second or meters per hour or whatever units are. It's a regular velocity unit for this. And F says, does the graph of position have any point of inflection points? All right, so now, since velocity is the derivative of position, when velocity is decreasing, that's when position will be concave down. So S of t is concave down from here to here. And when velocity is increasing, that's when S of t will be concave up. So we're concave up from here to here. Then we're concave down again from here to here. So we do have 2. Does it have any points of inflection? Yeah, at t equal 1 and 4. That's where velocity switches from increasing to decreasing or decreasing to increasing. So that hopefully that felt all right there. Okay. This one here gives us a function. We're supposed to find dy dx. We're going to do some implicit. This one's easy enough. It'll be 6x. This one's a little trickier, e to the xy. So we got to do the derivative of e first, which is its own derivative. Keep the exponent the same, times the derivative of the exponent, which is a product rule. So derivative of x is 1 times y plus x times derivative of y. This is where it's going to get a little crazy. Okay, plus y squared, that's 2y times dy dx, equals derivative of 13, which is 0. Okay, now I think what will be helpful for us is to distribute that, and so we're going to get 6x plus y e to the xy plus x e to the xy dy dx plus 2y dy dx equals 0. Now, if we subtract these over, we get negative 6x minus y e to the xy equals, and then we can pull this dy dx out, and it'll leave us with x e to the xy plus 2y, and then we'll divide that. So why don't we just go ahead and do that? And this will be our derivative then. So again, what I want you to do is look at the first line. Were you okay there? You know, doing implicit differentiation on that. This distribution is a little sneaky. Maybe you did it, maybe you didn't. But that's the key to then getting here. Okay. And then this one says, can you write an equation of the tangent line to 2, 0? So we already got the point. As far as the slope goes, what we're going to do is we're going to put 2 in for x and 0 in for y right in here. So if you do that, you're going to get negative 6 times 2, so that's negative 12, minus 0 times e to the 0 power over 2 times e to the 0 power plus 2 times 0. And that's going to give us negative 12 on the top, this zero's out, and 2 on the bottom, this zero's out, and that gives us negative 6. That's our slope. So y minus 0, or y, equals slope times x minus x. There's our equation.